I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for this class, and just ask you to bless our time today. Help us to learn more about power series and optimization, all this stuff. And again, just encourage the students if they're struggling, just to keep up the good work and just to continue their efforts. Lord, in your name I pray, Lord Jesus. Amen. All right, so yeah, this is day 2 of power series, and I want to complete the thought that we began yesterday, which is that we can take a function of 2 variables. Like here's an example of one, e to the x times sine y, and I can expand the x power series back in terms of calc 2 and the sine of y power series in terms of calc 2, and it actually makes sense to multiply these, all right? And you can multiply them and just kind of go order by order. Order 1, order 2, order 3. That's all I did it to. And there it is. That's the multivariate power series for e to the x times sine y up to order 3. Now I can look at this and I can tell you some things right offhand looking at it. Namely that the gradient of f is actually 0, 1. And let's see here, what else could I tell you? Well, let me just stop there for now. Now, let me try to, maybe it's not obvious to you why I can look at this and just see that the gradient of f is 0, 1 without further calculation. Let's try to understand that. So let's take a step back though and just talk about what would a power series in 2 variables look like just sort of generically. I would have constants, right? C0, C1, C2, C11, C12, C22, right? Like this. And you can see what would happen. If I evaluated at x naught, y naught, what would happen? Evaluating at x naught, y naught makes all of these terms go to 0, right? And it just leaves us with the first term. So the meaning of the constant term, that's the value of the function at the center of the series. Just like calculus 2, right? But what's the meaning of the higher order terms? Well, if we take the partial derivative with respect to x, we get c1 plus this and c2 plus that. So if I evaluate at x naught, y naught, again I pick up the coefficient as the partial derivative. And if I differentiate a second time, then I just get to this and that for the second derivatives, xx, xy, x as y, y, y. When I do that, and I put it together, I can write that f of xy is equal to f of x naught, y naught, plus this linearization, plus this quadratic form. Now the linearization we talked about before, it's just this right down here, which is, in particular, this is, well, okay, fine. Sometimes I've thrown the f of x naught, y naught into the linearization, so I guess my definition might be at odds with my earlier definition of big L. But anyway, that's just nothing more than the gradient right here, right? So I think I have a better formula for us to look at. Let me go on here. Yeah, here's a kind of better formula. It's hard to fit it all in one line using the x minus x naught notation, but like here, if you think of h being equal to x minus x naught, and if you think of k being equal to y minus y naught, this is what the formula for the power series looks like up to second order. So remember, this is x minus x naught, that's y minus y naught. So when I look at a power series, if there's a term which is linear in the variable, that's going to be the gradient, right? The term which is quadratic in the variables, that has to do with this thing I called the Hessian, the quadratic form part of the power series expansion. Here's an example. I look at the power series for the square root of 1 plus x plus y. I calculate the partial derivatives, like so. I evaluate at the origin. It gives me all these constants. I put it together. So here's the bivariate power series expansion for the square root of 1 plus x plus y. It looks like this. And so I can take this thing out for a spin and try to calculate the square root of 1.11. And I can look at that as 1 plus 0.1 plus 0.01 and use my handy dandy formula up here. And if I do that and do these exciting numerical calculations, right, I can get, what do I get? 1.0534875. And then in contrast, my calculator says that the square root of 1.1 is 1.05356. So where am I differing? I guess the third decimal place, is that right? 1, 2, 3. No, I got the 3 matching up. How about 5? I guess it's in the 4th decimal right here. I start differing, right? So I think that's pretty good for a third of a page calculation. Now, of course, you might wonder why you do this sort of thing. I always tell students that you have to imagine yourself in the robot holocaust, you know, where you have to do your own calculations. You can't trust the calculator. So you need a way to calculate things to high precision. Or you could imagine yourself an astronaut, you know, without calculational ability to the Earth, needing to calculate your trajectory on your lonesome. This has actually happened, right? Like midway to the moon, I think they lost communications. They had to do calculations on the fly. And that's okay, because astronauts are like PhDs in science who also can fly rockets, right? Any of you planning to be an astronaut? Okay, good. Because I think it's a pretty bad job. Anyway, so anyway, I mentioned this formula last time. Here's another example in terms of gory, boring detail, how to calculate all of those partial derivatives and put it together with this formula. Here out pops the multivariate power series. Now, is all this differentiation, that's pretty dumb, right? It's pretty dumb. Because what's a much faster way to calculate this formula? I just do what? I take the known Maclaurin series for cosine from Calc 2, and I just substitute xy into it. And I get the same result without having to take 4 derivatives. I didn't even show you the 4th derivatives here, right? There's more. All right, so let me show you a picture here. This is a picture of the power series. Well, it's a picture of the function that I just expanded up there, cosine of xy. This one actually defies our second derivative test, because all the second derivatives of cosine of xy are actually 0. I explicitly calculated them in the part I just scrolled past. But this thing, of course, it has a local maximum there at 0. In fact, it's a global maximum, right? Because cosine is bounded above by 1. And as you can see, it's, it's 1 here and here, because those are like the xy coordinate axes where you're plugging in 0 into cosine xy. So that's as big as it gets. Technically, that would fall outside the clutches of our second derivative test, which I'm going to show you here in just a second. Here's another one, sine of xy. It's got a power series expansion of xy minus 1/3 x cubed y cubed. Now this one, again, if you ask me about 0, 0, I look at this, there is no terms with just x or y on their lonesome, right? So I can see from just looking at this that fx of 0, 0 and f sub y of 0, 0, they're both 0. In other words, the gradient of f at 0, 0 here is 0. So the origin is a critical point for this function. But in this case, I think it's not going to be a max or a min. Now this one, we'll be able to use the second derivative test to test this one on. So let me make a note of that for myself. We'll come back to this one and apply the second derivative test to this in a bit, okay? Now, here's a picture of it. This, what you're looking at right now, I believe, is, I think it's that one. So what you're looking at, I need to find my, I really should put captions on things, right? All right, so yeah, that's the graph of the sine of xy function. Let me just try to explain the picture. The red is the approximating surface, and the actual function is the transparent wireframe. So this red would just be the terms, thanks Pablo, the red would be the terms in the, the red would be the terms in like z is equal to xy minus, I think, 1/6 x cubed y cubed, right? So like that's the approximating, goodness gracious, I guess it's 6th order polynomial, the red part. But the actual function you see in that transparent wireframe. So again, just like in calculus 2, the power series approximation is only good close to the point of the approximation, right? And as you get further away, it departs more and more from what you're approximating. That happens in the multivariate case too, and you can kind of see it here, right? it's like pretty close to the actual sine of x, z equals sine of xy function there, but as you zoom out and see what happens, of course the sine of xy function does all kinds of wiggly stuff. All right. You could also play these games in polar coordinates. If your function happens to be like a function of r, you could find the power series expansion in r, and then just substitute in the square root of x squared plus y squared, like you could do that. It would give you interesting formulas. All right, so let's move on here. Talked about these things yesterday. So here's the formula. This one is for 3 variables. So if you have the power series expansion at 0 for a function of x, y, z, the terms that are next to x, y, and z are the first derivatives. The terms which are next to x squared, y squared, z squared, x, y, x, z, y, z, these are the second partial derivatives. And it's a little bit fussy in terms of how things appear. Notice that there's a 2 that appears in mixed partial derivatives that's not in the double derivatives. So when you're trying to understand what partial derivatives mean for like second order or higher, you have to deal with these, like the disparity between the mixed partials and the double partials. Like identifying the meaning of the coefficient with respect to the partial derivative requires a little bit of thinking. But this much is true. If I have some multivariate power series expansion, right, and I've got like 3 times x squared, that means that the xx derivative divided by 2 is equal to 3, which means that fxx at the origin would be equal to 6 if I've got a 3x squared in my power series expansion centered around 0. Anyway, let's get to the point here. So, let's talk about critical point analysis. If we have a critical point, which is a place where the gradient of f is 0, then your function looks like this. It looks like the value of the function plus 1/2 plus the quadratic term, right? And that is a quadratic form, right? A quadratic form. In other words, this right here, this formula, and then plus higher order terms, which are smaller, right? If you're close, that's not a word. If you're close to the origin, right? If you're close to x naught, y naught, that makes this h and k, which again are x minus x naught and y minus y naught, that makes them exceedingly small. So the square is pretty small already. The cube is smaller still, right? The 4th power is even tinier. So this term right here is completely dominating the behavior of the function near the critical point. So we can focus our attention on that. And so the quadratic form we talked about last time with the Lagrange multiplier was something like this: ah squared plus 2bhk plus ck squared. So I can identify, for this quadratic form, thinking of h and k as x and y in my discussion yesterday, we can identify that this is my a, that is my 2b, and this is my c in the quadratic form formula. And so I can just use that result to analyze what happens here. So we had the formula lambda, right? Was this in terms of the coefficients? And if I plug in what I have, a equals b equals c, into these formulas and do out the algebra, I get this and that. And then, so basically this, this thing right here, traditionally, like in Stewart, for example, and pretty much all the other calculus books, this is called D. It's the Hessian. Just to point out what that is, if you've had linear algebra, great. If you haven't, it doesn't really matter too much. But if you look at the 2x2 matrix, fxx, fxy, fxy, fxx, fyy, like that, and you look at the determinant of this matrix, what is it? That wasn't me, was it? Okay, good. It's that, right? That is the quote-unquote big D of the second derivative test. And sometimes this gets called the Hessian as well, all right? And it turns out that if you're at a critical point, the value of this expression right here at the critical point pretty much determines the nature of the critical point. Let's see how that happens. So, but you see it appearing in this formula right here, right? So let's see here. So if d is goodness gracious, if d is less than 0, then I have, of course, this is equal to that. That's just square root, the absolute value definition. And if this is less than 0, then I'm subtracting something that's positive. Excuse me, my bad. If that is less than 0, then minus it is what? This is positive, right? This would be positive. So I'm taking this plus something. That's why this is greater than that. So as I said, this inequality indicates the radical dominates the sign of the solution. And so given d is less than 0, we have that the one lambda is negative and the other lambda is positive. That means that close to the critical point you have a saddle shape. If close to the critical point you have a saddle shape, then it's neither a max or a min, because you could be going up one way, going down another way. On the other hand, if d is positive, then we end up getting this inequality, which indicates that indicates that the sign of fxx plus fyy dominates the sign of the solution. In particular, if you work through it, either if this is positive, if fxx plus fyy is positive, then that means that both of your lambdas are positive. If both of the lambdas are positive, that means that the graph looks like a paraboloid which opens up close to the point of critical point. So it's a local minimum. If both of your lambdas are negative, it looks like a parabola which opens down close to the critical point. So both of your solution is local maximum. And if either of the lambdas are 0, well, then we can't say, because that means that the higher order terms are relevant. Like the third or fourth order terms might be relevant. If one of the lambda is 0, that means that contributions from the higher order terms could actually play a role. All right. So, and if you go back to my discussion of Lagrange multipliers, that means that cases 1, 2, and 3 of the general solution are relevant, whereas cases 4 and 5 are not, because cases 4 and 5 were the parabolic trough cases. Anyway, put this all together. Here you go. This is the second derivative test. Second derivative test simply says this, and this is what you need to know. If we have a critical point of f, all right, meaning that the gradient of f is 0 at the point, then you can calculate this Hessian, the big D, and if d is less than 0, then f of x naught y naught is not a local extreme value. On the other hand, if d is positive, and either fxx is positive, actually when you look at the details here, you can see that either you can check that the second derivative of x is positive, or it would also suffice to see that the second derivative of y is positive. They actually have to share the same sign in this context. So it's a twofer. They're either both positive or they're both negative. So, but typically calculus books tell you to test fxx because that's just the tradition. Then if they're both positive, and again it just suffices to check one, then the value is a local minimum. On the other hand, if fxx is negative, then the point is actually a local maximum. And this is the second derivative test. What were the derivative tests in Calculus 1? Do you guys remember? I know it's been a minute. Right? Yeah, we just check, is f prime of x, is f prime of like x not equal to 0? If it is, it's a critical point, right? Or it doesn't exist. But if it doesn't exist, we can't calculate the second derivative for sure, right? If you can't calculate the first derivative, you can't very well calculate the second derivative, right? As far as I know. At least in the calculus I know of. That'd be interesting if there's some kind of calculus where you could like not calculate the first derivative, but you could calculate the third and the fourth derivative. That'd be weird, right? I wonder if there's such a calculus. Anyway, okay, I should digress. No, I should not digress. Let's not digress. But in Calculus 1, there is another test. A better test, in fact, than the second derivative test. What is it? Before there was a second derivative test, there was a what?
First derivative test.
A first derivative test. Who's that at first? You get Slim Jim. There you go. Thanks to the person who left Slim Jims in the department snack room today. But do you like Slim Jims? Good. No. And it's packaged, so the fact that it landed on the floor doesn't matter. Okay, let me get to the point here. Why is there no first derivative test? Why is there no first derivative test for multivariable calculus? Why haven't we talked about first derivative test? Do you guys know? Any guesses? Is defined. Well, we're talking about critical points. I mean, critical point. It's everything's at a point here.
Like, why did we do the first derivative test in Calc 1?
Yeah. Why is there no? Why did we lose the first derivative test, or why is there no first derivative test?
Doesn't the first derivative test tell you it's increasing and decreasing?
Yeah.
Is it because we're in 3 dimensions?
We're in 3 dimensions. Right. So why did we also lose? There's another theorem we lost from Calc 1, right? Which was the limit at a point exists if what? The left and the right limits both exist and agree, right? It's that same issue. It's what you're just talking about. There's more than one way to come at the point, right? So a first derivative test here, if there was to be one, you would have to consider the infinity of different paths that were approaching the point. Now I do think if you could show that it's a maximum for every possible linear path going through the point, I do think that would be enough data to prove it's a maximum. I don't think we would be. I don't think we'd be up against the trouble we got into with the directional derivatives, not giving you differentiability, right? And the reason for that is that if you're talking about a critical point, you're already in the context where the derivative exists and the function's differentiable. So you've kind of already like smoothed over that issue. But anyway, I've never seen it written down, but it is true. One way you could analyze a critical point is to like look at all possible paths through it. And if for some reason you could actually hack that calculation, then you could say, hey, it's a maximum because it's a maximum with respect to every single path that goes through the point. Second derivative. So the second derivative test, on the other hand, there it is. Let's try it out for this function. So I should spend probably the next little bit of class on how do we find critical points, right? Because you guys need to work on like partial differentiation, and this is a great place to do it. A wonderful thing for most everyone in here to do would be go to section 14.7 and just work every single problem that's about finding critical points. If you do that, it will reinforce your basic partial differentiation, and you need work. Even people with high scores on this test made partial differentiation mistakes. Not all people, but many people. So here, what is fx? We differentiate sine, we've got cosine of xy, and then we have to do the derivative, chain rule, right, of xy, which is what? It's y cosine xy, right? Because the partial derivative of xy is just y. What's fy? Same derivative for sine, but now we've got the y derivative of xy, which just pops out at what? An x, right? So we get x cosine of xy. So what's the condition for critical points? We look for this being what? Both of these have to be 0 for a critical point. So my point to you is just that this is a nice place to practice your partial differentiation if especially if you lost a point or two on the second partial derivative problem on the test 2, right? I think at the end of this course, as you're looking back on mistakes you made on tests, that one will stand out to you as the one that could have been avoided. Because you won't make that mistake on the final. I believe in my heart, anyone who takes the final will not make that mistake again. Like, you will have partial differentiation down by then, for sure. And I'm sorry if I haven't assigned enough homework towards that end. I don't know. If I assign too much, then you guys stop doing it too, There's a balance. which I don't always find. Okay, so can you solve these equations? Here's one easy solution, right? Easy solution. How about this? X equals to y equals to 0. That definitely works, right? So the origin is a critical point for this function. Origin's a critical point. And now let's calculate fxx. I'll be right back. do 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 Slim Jim for your trouble.
Oh,
There you go.
you.
Hmm? Oh, you don't want it? Okay.
Meat stick guy. Sorry.
All right, so the x derivative would be minus y squared sine of xy. Why do I have a y squared there? Right. Chain rule gives me a second y. How about fxy? We get minus, is it xy? Sine of xy. Oh man, I have bad feelings about this example. This one is what? Minus x squared sine of xy. Well, this is a bad example. Why is this a bad example? Oh man. Dang it, I should have expected this. What's d then? Well, d of 0, 0, what is it? Plug in 0 to this, what do you get? 0. Plug into fyy, what do you get? 0. fxy, 0. The d is 0. And what does the second derivative test have to tell you about d being 0?
Nothing.
Tells us nothing. And could I have expected this without all this calculation? I totally could have, right? Because, check this out. F of xy, sine of xy. Can we find the power series expansion of that? Well, yes, we can. It's xy minus 1/6 xy cubed, right? Plus dot 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 dot. And what that is xy minus 1/6 x cubed y cubed plus dot 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 dot. What I can tell you from that expression, just looking at it, is that every partial derivative of order 6 or less is 0, except for fxy. Well, why is that not 0? Hold on a second. No. No, this means there is a second order derivative which is non-zero. All the other ones are 0. See, the next non-zero one is this fxxx, fyyy. This tells me that like fxxx, y is not equal to 0. And now to figure out the actual value, I have to figure out the combinatorics of how many times that term appears. And that would take me some time to figure out. But this should not be equal to 0 at 0, 0. Again, this is at the origin. So we have made a mistake up here, right? Product rule, yes. So, of course, after I give you guys a lecture about not doing the product rule, I make the same mistake. Of course, but in my case, it was on purpose so that I could show you the utility of this way of thinking. You're welcome. And so let's see here. Differentiate. Let me just write it out here. Differentiate with respect to y, fx. fx was y cosine xy. Okay, there we go. It is indeed a product. So I have cosine of, oh, thank you. Cosine of xy, yay, minus y squared sine of xy, which is what I had before, I think. Or is that minus, is it y squared? I think it should be xy. xy, minus xy. All right. So now, what's my d equal to? The d of 0, 0 in this case would be equal to fxx at 0, 0, fyy at 0, 0, minus fxy at 0, 0 squared. Also known as what? Negative 1. Is negative 1 less than or greater than 0? This is an easy one. It's your time to shine.
Less than.
Less than, okay, very good. So we're definitely in case 1, which says what? It says that the origin, f of 0, 0, is neither a max nor a min for this function by the second derivative test. This is missing a title. This should definitely have second derivative test here. So if I had an editor, that would have been fixed, but I don't. So my editor is you guys, but you guys never complain. That's not true. You complain, just not about, not constructively about these things. Not usually, anyway. Any questions? Here, let's look at an example with a little bit more. Now, a much tougher question would be, is that the only critical point? There's other critical points here, right? What are the other critical points? Yeah, when xy is pi halves, but actually, there's a whole infinite family of them, in fact. If we have xy is equal to, pi over 2 times 2k plus 1, where k is an integer, that is a critical point. Any half integer multiple of pi, basically plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, plus or minus 7 pi over 2, and on and on and on. The question is then, can you see what is the Hessian at those points? Ew, that's so much worse than I was thinking. Is that a point? No, man, that's this. Ooh, ah, e. This function is critical along an infinity of points like this, like that, 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 because these are reciprocal functions of various, like the first one, the pi over 2 one would be like this one. Maybe y equals pi over 2x would be this one. This is y equals to 3 pi over 3 pi over 2x. This one would be like, the lowest one here would be y equals minus pi over 2x. That's this one too. And listen, some of these, and these are going to be min max, 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 min max. Why? Why are these mins and maxes, mins and maxes?
Its sign changes every other time.
Right? But well, let's just take a step back here and think about the formula, sine, right? If I plug in pi over 2, right? Or 5 pi over 2, what do I get? I get 1, right? So I'm going to get 1 when I plug these into sine, or I'm going to get minus 1. So in fact, these are all mins, I think, because I think we have sine is minus 1 along these. And these are all maxes because we have, we have sine of 1 on the red ones. We have sine of minus. Sine is minus 1. If I'm thinking through it correctly. Like sine of minus, what, yeah?
So sine curve would maybe a peak and then drop, peak and drop.
Well, that I mean, I'm not, in 3 dimensions, that is what's going on. It's, yeah.
So how about this?
Hey, we're supposed to have a quiz. So I better get you guys a quiz. What's that? So anyway, we'll talk more about the second derivative test Monday and the closed set test, but we'll probably look at examples Monday. The theory's done. Like, that's it for the theory. So sorry it took me so long. My bad. So I am going to help you guys with this one. So I'm not going to collect this one. I'm going to assume that everyone gets full credit on this one, if that's okay with you guys. This has nothing to do with the viral pink eye I heard about, just for the record.
This is just for fun.
I mean, it's for score, so yeah. But we should work through this together, yeah? Let's work through it together. So I think you guys can figure out problem 1. Let's focus our attention on problem 2. Can you guys tell me, look at problem 2, and you guys tell me, is it a critical point or not? What's the gradient at 0, 0? Is it 0, 0 or is it 1, 2, 3? I can't remember. I did. All right. So is the gradient at 1, negative 2, 3? Is it 0? Is it non-zero? How do you know? It really goes back to the formulas I wrote yesterday. I'll write it out again today. So like f of x, y, z would be f of x naught, y naught, z naught plus f sub x of x naught, y naught, z naught. I'm just going to call that p naught times x minus x naught plus f sub y of p naught, y minus y naught plus f sub z of p naught, z minus z naught plus 1/2 fxx of p naught x minus x naught squared plus 1/2 fyy of p naught. Man, I'm getting tired of writing this. Y minus y naught squared. Why didn't I do this for 2 variables? I'm a dummy. zz p naught z minus z naught squared. Plus fxy of p naught x minus x naught plus f xz of p naught times, oh come on, y minus y naught. So what did you guys think while I'm suffering this fate of unending formula? The linear terms are trivial. So what's that mean? The gradient is what? 0. Which means it is a what? It is a critical point, yes? My apologies for the double plus, as usual. Actually, double plus. It's doubly offensive, depending on your counting. All right, so let's talk about this here. This guy, as you pointed out, gradient is absent. I mean 0. So is this a critical point? Now, you're like, well, but this is not this is order 3. You can't ask this, out of bounds. No, this is within bounds, and the reason it's in bounds is you can just use your brain. You can just think. If I'm close to the point 1 minus 2, 3, right? And I go a little bit away from it. Does the formula get bigger or does it get smaller? If I plug in like 1.1, comma, minus 1.9, comma, 3.1, you've got what? 3 plus something. So is this a local minimum or a local maximum? Minimum, right? Because if we go a little bit away, we're getting bigger, which means that at the center, we're smaller. So this is a local minimum. Yeah.
Wouldn't we also need, to know that, wouldn't we also need the x, y, x, z, x, y, z?
Oh, well, when I write this, it's under, yes, very true. And so to make this problem unambiguous, I really should add a third order term just to seal the deal, to be clear. That was my intention, that this is the totality of the quadratic contributions. If I did have an x minus 1 times y plus 2 term, then at that point I would have violated the terms and conditions, my promise to you, which is not to require linear algebraic calculation in calculus 3, which is what that would require. If there's the minute there's a mixed term, we would need a second derivative test for 3 variables, which you will not find in books. Because it would just be so onerous. It's so difficult to write that down. Yeah.
Why isn't fxx 8?
Why isn't what?
fxx.
fxx
Yeah, like the second derivative.
at the point?
Well, it seems like it would be a constant 8.
Well, that's true. fxx at the point, I mean, you're not wrong. I didn't ask that here, but we could say that fxx of 1 minus 2, 3 is equal to 8. The reason I could say that is because that divided by 2 has to be equal to the 4 here. As to why the second x partial derivative is not just identically 8 for all x, the answer to that is in all of the terms I didn't write down. It's in the plus dot dot dot, so you can't see it. Trust me, there's variability there. All right, so if we have time, we'll circle back to problem 1, but I want to make sure we talk about these ones because they're kind of the more interesting ones for Calc 3. Aw, man. Sorry those are not here. I was focused on the other board. My bad. Oh well, I will write a solution to this so you can look at that, but I haven't written it yet. So what do you guys think about this one? Is the gradient non-trivial here? What do you think? How do we figure out the gradient? Here's what we don't do. We don't actually partial differentiate this. You could do that, but that would be foolish. There's no need. By inspection, I can tell you, looking at this, that 2 is f sub x of 3, 4. That's the meaning of that coefficient. By inspection, I can tell you that f sub x of 3, 4 is 2. And what's f sub y of 3, 4? It's 6. So is this a critical point? The gradient's non-zero, so the answer is no, not a critical point. Right? Which means that the graph is not at a max or a min or a saddle. It's just kind of going some kind of slopey way. Whatever. Now, we can calculate the second partial derivatives at 3, 4. Looking at this, what do we have? So you have to kind of, it's the same formula for two variables. So it's like 1/2 for the double derivative, but there's no 1/2 for the not double derivatives. So like with that in mind, we have the equations fxx at 3, 4 divided by 2 equals fill in the blank, fxy at 3, 4 equals fill in the blank, and finally fyy at 3, 4 divided by 2 equals fill in the blank. So you guys fill in the blanks for me. It's just pattern matching. See? The 1/2 x squared term that's here, that makes me put a minus 1/2 here. How about xy? That's here. I get a 3 there. Yy? I've got a 10. So you guys can then easily figure out that fxx is -1, fxy is 3, and fyy is 20 at 3, 4. Again, I would like to emphasize, you don't actually need to do two partial derivatives to learn this. You can see it if you know the meaning of the coefficients of the expansion. We can just read from the expansion directly. Whenever I ask this question on the next test, like I have 70% of the class just taking partial derivatives, burning all kinds of time they don't need to burn on that. Now this one here, finally an actual find the power series. So how should we do this one? What do I need? I mean, there's some fairly obvious stuff going on in this one, right? Like, did I pass the attendance sheet around? I should do that because this attendance means that you got a 12 on the quiz. So, actually, I guess we only finished 3 problems. Everybody should get a 9, right? Messing with you. So here we go. We've got y plus z, or is it over 1 minus x plus, what was it? X cos y. How do we do this? So what I'm going to do is I'm going to do y plus z times 1 over 1 minus x. Think of it that way. And then, well, x, what's cos y? It's 1 minus 1/2 y squared plus the next order term is order 4. I just said for us to do it to what? Order 3 at the origin. So that'll do. You know, an important principle of power series calculation is not to do more than you need to. And the other one's geometric, right? So what are we up against? Y plus z times 1 plus x squared plus dot 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 plus, this is x minus 1/2 xy squared plus dot 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 dot. Multiply this out, you got yourself a y plus z plus xy, well, x times y plus z plus x squared times y plus z. I think that's it. And then we just need to like collect terms. Let's see here, all the linear terms are y plus z. Quadratically speaking, I just got plus y plus xy plus xz. Oh, I missed my x over here. So x plus y plus z plus xz. And then third order, x squared y plus x squared z minus 1/2 xy squared. So I think that this is it for order 1. This is it for order 2, if I haven't missed something. And that's it for order 3. Anyway, I'll write a solution for this. If I made a mistake, I'll find it there, I hope. But I know you guys got to go. So have a good weekend. Sorry if this quiz wasn't as scary as you had hoped.